Hi, my name is Bill Fortney, and it's an honor to lead you on this journey learning about engineering statistics. It's a topic that I'm very passionate about because I have used statistics a lot through my career to save money, to make good decisions, and I'm really glad to be able to help pass on some of that knowledge to you to help you use statistics to be a better engineer. Okay, so to get started in this session, we're going to be looking at why engineering statistics. Why even bother with it? And to start, I want to look at what do we really do as engineers? What do we really do? And what we do is we solve problems. We make decisions and we spend money. It doesn't matter whether we're doing a design, whether we're doing an engineering investigation, whatever it is, we are making decisions, and those decisions affect things that spend money. And in order to make good decisions, we need good information. Engineering is all about fact-based decision making. We don't guess, we use facts. And good decisions require good facts. So how do we get those facts? Well, if it's a person, we go and talk to people. And depending upon their answer, we may go talk to some other people. If they sound a little uncertain, we're not sure, we'll go talk to people, talk to someone else, talk to someone else. We will keep exploring until we've got that warm, fuzzy feeling inside that we have solid information, we have good facts, and then we can go and make a good decision. But what about if what we need information from is a thing, an item? We might be able to research and find out about that item, but often we have to collect data. We have to go to that thing, whether it's a helicopter part that's wearing, whether it's a circuit, and that we're wondering about how much power it's drawing. We have to be able to ask, what can I expect from you? So we measure, we analyze data to gain information to make a decision. And you always want to remember that with data analysis. There's always a decision at the other end. And that's going to drive the kind of accuracy that you need. That's going to drive how deep you go into the analysis is what's riding on the decision. And we're doing it in order to solve a problem. So that's why we need good information. And what I want to show you in this video is that without statistics, you can't get the information that you need from a thing for a good engineering decision. So let's start with an example. Let's say you're doing a design and you need to know how much a bolt will hold. There's going to be a certain load on it, and so you need to size the bolt. You sized it and you need to check how much it will hold. And so it's pretty easy. You go look up the standard, and let's say you're using a grade 8 bolt. You can come right down here and see that, okay, it will hold 150 psi is the ultimate, the tensile strength. Bam, you know, you have the information that you need. You know exactly what to expect from the bolt, what you can count on. It's never going to be less than 150. You can go base your design on that. Now let's turn the tables a little bit, and let's say that you work at the factory that's making those grade 8 bolts. How do you know that all of your bolts are 150,000 psi? In fact, your manager, he tasks you with keeping them out of jail. Now, what do I mean by that? With determining if your factory is always producing bolts within that specification of 150. Because if not, your manager is going to be in trouble because someone is going to buy that bolt, they're going to use it, count on it being at least 150. If it's not, there could be an accident, and then your manager is going to be liable. So you need to ask your factory, what can I expect from you in terms of the ultimate of grade 8 bolts? Obviously, the factory can't talk, so you're going to go and you're going to collect some data. You're going to take bolts from your factory, you're going to put them on the tensile tester, and you're going to see what their ultimate is. And there it is right there. And first thing I want to ask you is, notice this number here is different from this number here. Does that surprise you? Does that surprise you that all these 30 numbers aren't exactly the same? And I'm guessing you're going to say, well, no, it doesn't surprise me. And it shouldn't. So, but why are they different? And there's a couple of reasons. First of all, just because, and this is probably why you weren't surprised. There is variation in everything. The raw material that they're using to make the bolts, there's some variation in that. The furnace temperature, when they're heat treating it, there's some variation in the furnace temperature, just like your AC at home. It goes up, it reaches a max, it comes back down, there's variation. The cooling and ambient temperature, we could go on, but everything, any item with a dimension, with a characteristic, has variation in everything. So no, we're not surprised that those are different. There's a couple other reasons they could be different. And well, all of those things together work together to create what we're going to call in statistics common cause variation. You also hear the phrase random variation. Okay, so why are they different? Well, one reason they're different is just random variation, just because. They could also be different because of measurement error. Right now, we're going to rule that out because we're going to design our experiment in a way where that's not a factor. The other reason they could be different is something changed. We call that special cause variation. Like you got a new furnace for doing heat treating, or you got a new vendor for your raw material. Right now, number 2 and number 3, we're going to ignore. The only reason these numbers are different is common cause variation, random variation. So, one thing I want to make a note right here that you'll see through everything we do, through all of your labs, you want to remember there is variation in everything. So that means you can't just take one sample and use that number for a decision. Because just think, if you got this number right here, 153, you think, oh, well, that's kind of low. Or if you just got this one number, 155, you think, oh, no, you can't just use one number and think you have an idea of whatever it is you're trying to measure because there's variation in everything. All right, so we have these numbers. They're only varying because of pure random variation. We know how much it needs to hold, 150,000. So now, what number do I use over here of all of these for my decision? What number do I use to tell me what can I expect from my factory in Ultimate? I could calculate some things you might be familiar with. I could calculate the average of all these numbers, the standard deviation. I could calculate the maximum. I could calculate the minimum. And we might look and say, okay, the minimum I get is 159.30. It's higher than 150, so my factory is producing above that. My boss is going to stay out of jail. But we have a problem, and a serious problem in terms of your boss staying out of jail. We don't care about just these 30 bolts. We care about all the bolts coming out of the factory. This minimum is only the minimum for these 30. If we went and took another 30, we're probably going to get a different minimum. Remember, there's variation in everything. What if I tested 30 more parts? Yep, I'd get another minimum. So, if we tested 100, still, we're going to get a different minimum. So, we've got a problem, and that's where we need statistics to help us say, what number do we use that would consider all the possible samples and tell me what to expect? That's where statistics comes in. Now, what I can tell you with statistics, number one, is this minimum right here of 159.30. It's not the full picture. There's a 2.8% chance that a bolt from our factory will be less than that 159.30. That's 28 parts in 1,000. That's a lot. So, with statistics, we can consider all possible samples and know what to expect. And so here's what it can tell us. We need to hold 150. There is a 3.5% chance that our factory will produce a bolt less than that 150. That seems really small, but that's 3.5 bolts in 1,000. That can't happen. Because remember, you're counting on that bolt to never be less than 150. That's the fact that you're using in your design. So, yeah, the way we're operating right now, our boss may go to jail, so we need to do something. So let's say I took 30 samples a whole bunch of times, and I kept getting very similar to all these same numbers right here. So I'm pretty sure I have good numbers for these guys right here. So if that's the case, and let's say I had a knob to turn, like where if I could turn this, my factory, the ultimate would go up. Based upon statistics, what I would do to keep my boss out of jail, and you will learn how to calculate this, is I would turn this average from 154,002 to 160,346, and then I am very confident that we would never produce bolts with an ultimate below 150. My manager's not going to jail. That's what statistics can tell us and can help us. And that's exactly what real bolt manufacturers do. This graph right here is bolts, grade 8, quarter 28 bolts that we bought from McMaster, and we tested them in the tensile tester. And there's 3 different years that we tested them, 3 different groups of students. And notice they're way up here at 170. I said I would set it to 160 something. They're even a little higher than that. They are taking no chances that their bolts are going to be below 150. How did they set this? They used statistics based upon the characteristics of their plant. Okay, so let me give you another example. There's a phone holder project, and the way this phone holder works is this center piece right here is threaded. In fact, right here you can see the stud going through it, and then the shoulder bolt, and then a wing nut right here. And somebody has the idea, instead of milling these, because right now these are made on a milling machine, very time intensive, someone says, look, could we 3D print these parts? And it's a great idea. If we are a company making these, that would save us an enormous amount of money. So we'd like to look into it. We're tasked with looking into it. So the real question is will the threads hold? So for that decision, what do we need to know? Number one, we need to know, okay, threads in this 3D printed part, how much will they hold? And then the second thing we need to know is how much force does it need to hold? Somebody tightening this wing nut, how much force pulling out can they put on? So the first question, how much can the 3D printed part hold? We say, well, look, why don't we 3D print some parts, thread things into them, put it on the tensile tester, and pull and see what the ultimate is. So we did that. And we did it with Delrin, which is a solid material that we used to use to make these. And then we did it with 100% fill of the material that they'd be printed on. And so you can see the numbers right there. And the same kind of question we had before, well, what number do I use for my decision? Then for how much force does it need to hold? How much can somebody torque that wing nut, and how much will it be pulling out? First thing we did is we researched, and we found some information, we found some forces, but we wanted to triangulate it. What does that mean? That means we wanted to look at how much force from a different angle to make sure, because the research is a little vague. So we did testing. So we built a little apparatus, had a load cell right here, and there's the wing nut. And so we would have people come and tighten that wing nut, and then we recorded the amount of force that it was pulling on that load cell. And here that is. And again, what number do I use for my decision? We could, again, calculate numbers. We could get a minimum over here, a maximum over here, but we've already seen it can hold 294. It only holds 293. That's close, but yeah, it might work. But we saw before, we don't just care about these parts and these parts. This is only the minimum for this sample. This is only the maximum for that one. If we tested 30 more people, we would get different numbers. So again, in order to know what number to use, what we can expect that would consider all possible samples, we need statistics. Again, statistics tells me a few things, like number one, it tells me that there's a 2.9% chance that we could get a part below that 294.68. Again, that's 29 parts in 1,000. That's a lot. And there's a 1.8% chance that a person will put more force than that. That's 18 in 1,000. So, considering all possible samples, how could statistics help us in this case? Well, it can tell us that with 99.9% certainty, all the values will fall in these ranges. I could actually get more confident. If I wanted 100%, I could get that and get a different range, but 99.9% of the values are going to fall within these right here. And what that's saying is, like, it would not be unreasonable to expect that I would have parts that could only hold 242. If I was 3D printing them, because of the variation, it would not surprise me to get parts that would be 242. It also would not surprise me for a person to come up and to be able to put 330 pounds on that. So when I look at this, I don't need any more information. I can get a 242 for how much it can hold. I can get a 330 for what it needs to hold. 3D printing is not going to work, okay? But you see the power. Statistics gives us the information that we need to make good engineering decisions. Whether that's telling us the lowest number we can get, the highest number we can get, the average value, whatever it is, what percentage it is, it's going to fall below it like we did before. Statistics can tell us that. Okay, so one more example. Let's say you're on a design team creating a very sophisticated facial recognition system, and you're designing one of the many circuits in this system. So some of the other components in the system are very sensitive to heat. So you've been asked to give the amount of heat that your circuit will generate. Now, you might be able to do some calculations, you might be able to do some research, but it's likely that you're going to have to create some prototype circuits and perform testing to understand the amount of heat that your circuit is generating. And since there's variation in everything, you know you can't just test the heat from one, so you're going to measure many boards, and the data that you're going to get is going to resemble what we had from the bolts. You're going to have a lot of different numbers, and you're going to be left with, what number do I use for the heat generated? And just like before, you need statistics in order to tell you, okay, considering all the possible things that can happen with multiple boards, what is the maximum value that I can see? So you then can tell people, okay, this is the maximum amount of heat that you will see from my board, and they can use that to determine how much heat transfer that they're going to have from the vessel that's containing this, okay? So you see, statistics is important for us because the fundamental question we're going to ask of a thing is, what can I expect from you? And because there's variation in everything and some other reasons we're going to learn about, without statistics, it's hard to answer that question. But once you do answer it, then we know what to expect, and you can go on and you can make your engineering decision. So why do we need engineering statistics? Because we need good information from a thing to make a good engineering decision. There is variation in everything, so we can't just collect one data point and know what to expect. Well, to determine what to expect, we're usually going to collect data from a subset of all possible occurrences. We don't have all the bolts. We only have a subset of them. It's called a sample. And so we need statistics to allow us to look at our sample data and attain a reasonably good idea of what we can expect from all of the other data that we didn't see to know what we can expect from our thing. So that is engineering statistics, and why any kind of decision making, any kind of exploration that we're doing where data is involved, we need it to give us good information. So what we'll do from here is, first, we're going to learn some foundation, just some foundational statistic information. You can kind of call it theory, but you're really trying to gain a conceptual understanding. Then we'll talk about real-world data collection, data analysis, making decisions using statistics. And when we do the second part, it's critical that you have a conceptual understanding of the foundations. So as you're going through, understand the math. It's not real hard, but make sure that you pay attention and that you conceptually understand the topics that are being presented. And if you don't, go back, look at the videos again, so that when we get to the second part, you will have the tools that you need to really use statistics effectively to be a good engineer, given all of the challenges that you're going to see the real world brings. And I look forward to continuing on in this with you.